Good day, everybody. Today, we'll be talking about molecules and compounds. Previously, we have already learned a compound is made of two or more elements in a fixed, definite proportion. Actually, this is summarized by the law of constant composition. This law states that all samples of a given compound have the same proportions of their constituent elements. This means for any sample, no matter where you find it and how you find it or how you made it, they must have exactly the same fixed, definite proportions. For example, for water, no matter where you find it or how you make it, they will always have the same ratio. For 18 grams of water, you will always have 16 grams of oxygen and 2 grams of hydrogen. So the mass ratio between oxygen and hydrogen will be 16 grams over 2 grams, which gives you a ratio of 8. And this is true for any sample of pure water, no matter of its origin. Although the mass ratio between different elements in the compound is definite, but usually we do not use the mass ratio to represent the formula. Rather, we use the number of atoms, use their ratios. For example, in water molecule, H2O is the chemical formula. It indicates that water consists 2 hydrogen atoms and 1 oxygen atom. Their ratio is 2:1. So when we write the formula, we write H as the hydrogen element and O as oxygen element. To represent 2 hydrogen atoms versus 1, we write a 2 as the subscript for hydrogen, and the 1, which is the subscript for oxygen, is usually not written. Remember, subscript 1 is usually not written. Let's look at a few more examples. For example, table salt, or NaCl, it indicates the ratio of sodium and chlorine atoms is 1:1. That's NaCl. Notice the 1 as the subscripts are not written. CO2, that means for every carbon atom, you have 2 oxygen atoms. For table sugar or sucrose, the elemental ratio between carbon, hydrogen, and oxygen is 12 versus 22 versus 11. You might have noticed all these formulas are written in a certain way. If so, you are absolutely correct. When we write chemical formulas, they have to be written in a certain way. For example, if in the chemical formula you see metals, those metallic elements must be written first. So in NaCl, you must write sodium first because it is the metal. If you write Cl and A, that's wrong. Another mistake is some students like to write 2 uppercase letters. That's also wrong. For any element, you must have 1 and only 1 capital letter, which is the first one. So the second one, if it belongs to the same element, it must be the lowercase. So it must be NaCl. If a compound does not include a metal, then the more metal-like element is listed first. Remember, in the periodic table, metals are found on the left side of the periodic table, with the exception of hydrogen, and nonmetals on the right side. For nonmetals, those to the left in the periodic table are more metal-like. For example, when you look at the periodic table, nitrogen is to the left side of oxygen. So that's why we write NO2, not O2N. O2N is wrong. The elements in the same column can be compared by looking at their order as well. The elements toward the bottom are more metal-like, thus they should be written first. For example, sulfur is below oxygen, so in SO2, it should be written in the order of SO2, not O2S. If the elements in the same formula are neither in the same row or in the same column, we also have an order of listing, as you can see in the next slide, right over here. So usually we write carbon first, then we write phosphorus, nitrogen, hydrogen, sulfur, iodine, etc. For example, if you want to write a compound between a carbon and hydrogen, for example, methane, you would write it as CH4. If you write it H4C, that would be wrong. Another example, between phosphorus and hydrogen, it forms a compound, PH3. You should write it as PH3, not the opposite order. Give you a few more examples. For example, if you form a compound like a BrCl, which does exist, it should be in this order, not the opposite, which is Cl, Br, and that would be wrong. Okay. So we have talked about how to write the formulas in the correct order. In the previous slides, we also talked about how to count the number of atoms by looking at the corresponding subscripts, but we do have more complicated situations. For example, you might run into a formula that has parentheses. Do remember any subscript. So for the subscript, it can indicate two things. It's the atom, it indicates the atom right before that subscript. That's one way, unless you have a parenthesis. If you have a parenthesis, the subscript refers to everything inside the parenthesis. Okay. So, or the elements in the parentheses. So for example, in magnesium nitrate, you see the formula over here, right? I'm going to rewrite this thing. It's MgNO3. Any subscript can only refer to either the atom right before it or the parenthesis right before it. So for this 3, it can only refer to 3 oxygen. It cannot be extended to nitrogen. No. However, this subscript 2, it can be extended to nitrogen because nitrogen is also inside the parentheses. So this subscript 2 refers to 2 NO3 units. So if we want to count the number of magnesium, magnesium would only have a subscript of 1, which is not written. So that's why you see magnesium counted as 1. Okay? Nitrogen, inside the parenthesis, you have NO3, which contains 1 nitrogen, but you do have a subscript 2. So that's why you have 1 nitrogen in NO3, but you have 2 NO3 units. That's why you multiply by 2. This gives you 2 nitrogen. Similarly, for oxygen, remember, in this oxygen, after that, you have a 3 attached to it as the subscript. So in each NO3, you have 3 oxygen. However, you do have a subscript of 2. That's why you get this 2. So the total is 3 times 2, which gives you 6 oxygen atoms. Let's work on one example. Again, I'm going to suggest you work on this first and pause the video for a little bit before you continue. This question asks us how many hydrogen atoms are in the formula. So when you look at the formula, do you remember this number 4 only refers to the hydrogen right before it, because there is no parenthesis before that number 4. All right. However, for this number 3, it refers to the whole unit of NH4. For this reason, the number of hydrogens can be calculated this way. In each NH4, you have 4 hydrogen, and you have 3 as the subscript for everything inside the parenthesis. That's why you multiply this by 3. So you would end up with 12 hydrogens. So E is the correct answer. Let's look at another example. What is the hydrogen to carbon mass ratio of methane? I want you to read this really carefully. This is not asking you the ratio for the number of atoms. If that's the question, it would be 4 hydrogens versus 1 carbon. Then the ratio would be 1. Okay? However, here it's asking you the mass ratio. So it's asking you the mass for 4 hydrogen versus 1 carbon. What is the mass for 1 hydrogen? 1 hydrogen, you have the atomic mass of 1. For 1 carbon though, again you have 1 carbon, but each carbon weighs 12 atomic mass unit. So when you do this, that's 4 over 12, which gives you 1 over 3 or 0.33. That's the mass ratio. So when you read the question might look very straightforward, but please read it very carefully and figure out what is being asked so you don't make a simple mistake. So far, we have learned how to correctly write the chemical formula in the correct way. We also learned how to count the correct number of atoms in each formula. Now, we are going to talk about the different ways to represent chemical formulas, or the different types of chemical formulas. Empirical formula gives the relative number of atoms for each element. Remember, it's the relative number, but I'm going to make it more specific. It gives you can do it in another way. It tells you the smallest whole number ratio of each element. So for example, if you have a formula that looks like this one, N2O4, okay, apparently it's not the most simple ratio. This one is the chemical formula. Let's say that's the chemical formula, which tells you in this formula, you have 2 nitrogen atoms and 4 oxygen atoms. So what is the empirical formula? The empirical formula would be the most simple ratio. So if we divide 2 by 2 for each atom, you would end up with N1, which 1 is not written, so it would be NO2. NO2 would be the empirical formula. All right. Then what is the molecular formula? Molecular formula is the chemical formula for molecules. Okay? NaCl is not a molecular formula. It's an empirical formula because it tells you the ratio between sodium ions and the chloride ions. It does not. In ionic compounds, there is no molecules. So molecular formula is the chemical formula for a molecule or for a covalent compound. So this is more specific. A molecular formula is referring to the chemical formula of a covalent compound. So what is covalent compound? A covalent compound is formed between nonmetals. Look at another example for hydrogen peroxide, which is H2O2. The empirical formula would be HO. What about another example? For example, C12H22O11. if this is the chemical formula, this is the chemical formula, what would be the empirical formula? Or you might be tempted to divide by 11 for hydrogen and oxygen only, which you end up with 12. Yeah, I'm going to divide the other two only. This would be totally wrong. If you want to divide by 11 or by any number, all atoms must be divided by the same number. However, when you divide 12 by 11, this does not give you a whole number. So this just tells you C12, H12, O11 is already the most simple ratio. Or in another word, the chemical formula in this case is exactly the same as the empirical formula. So the empirical formula for this table of sugar is the same as the chemical formula. This is also the empirical formula. Okay? All right. There is another type of formula which is called a structural formula. We use lines to represent the chemical bonds and shows how the atom in the molecule are contracted to each other. Let's look at methane as the example. In CH4, this tells you 1 carbon and 4 hydrogens are combined to make a molecule, and this is so-called a molecular formula. You can also call this a chemical formula. Okay, and this chemical formula is for a molecule, so that's why it's also called a molecular formula. And the structural formula in this line, single line, that tells you it's a single bond being formed between carbon and hydrogen. We have another model that is so-called ball and stick model. In the ball stick model, we represent the balls. Okay, the balls are representing atoms, and the sticks are representing the chemical bonds being formed in between the atoms. In the space filling models, atoms fill the space between each other to more closely represent our best idea of how a molecule might appear if we could scale it to a visible size. Another important aspect about the ball and stick model or the space filling model is that the atoms are color-coded. For example, we use white to represent hydrogen, and black to represent carbon, and blue for nitrogen, red for oxygen, etc. To sum it up, there are many different types of chemical formulas. For example, empirical formula, molecular formula, molecular models in terms of a ball and stick model and a space filling model. And you need to know what details they can give you and what information you can derive from that structure, the drawing, or that formula. Now let's switch gear and talk about the details about how to classify elements and compounds. In previous chapters, we already know a pure substance can be classified as either an element or a compound, depending on the number of different elements you have in that pure substance. An element is made of one type of atoms, and a compound is made of more than one type of atoms. So, what about the details? If an element is composed by atoms only, then we call this atomic element. For example, neon, helium, right, or copper, or sodium, they are all atomic elements. We'll go into the details about how do I know which element is atomic, which one is molecular, or more details, which one is molecular and it's composed of two atoms. Then we will call that the diatomic molecules. What about triatomic or polyatomic We'll go over that in the next slide. For compounds, there could be a molecular compound. We explained what is a molecule. A molecule is formed between nonmetals by forming the covalent bonds. An ionic compound is usually formed between a nonmetal, a metal and a nonmetal. For example, table salt, NaCl, Na is metal, Cl is nonmetal. So that's why this compound, NaCl, is so-called ionic compound. Molecular compound, for example, water, H2O, formed in between nonmetals. So elements could be atomic or molecular. For the details, let's look at the periodic table. All right. Most of the elements, do you remember? Most of the elements, they are actually atomic, or they simply contain one atom in the formula. Okay. But how do we know which one is? So let's start with actually the so-called diatomic elements. Okay. So here, this tells you diatomic elements. Number one, I'm going to label it as number one. And this is so-called a rule of 7 because there are 7, 1, 2, 3, 4, 5, 6, 7. 7 common diatomic elements over there. Okay. And in the periodic table, 6 of those 7, if you look at the periodic table, this is hydrogen. And for the 6 of the 7 elements, it makes a nice number 7 out of it. So that's why this is so-called rule of 7. You have 7 common diatomic elements. And the second thing you need to know is there are also some polyatomic. Okay, so for polyatomic elements, again, we're focused on elements right now. Okay, we're not talking about compounds. Polyatomic ones, there are a few of them. I'm going to single them out for you, and you will simply have to memorize it. For example, for oxygen, which is diatomic, but it does not exclude the possibility for a triatomic, which is one of the polyatomic. Okay, so oxygen is kind of special. It can be diatomic, it can also be triatomic. And for phosphorus, it's actually P4, and sulfur is S8. So that's the only 3 that you need to memorize. All right. Then what about all the other elements? Oh, if you remember what is diatomic and what is polyatomic, then for the monatomic or simply atomic, all right, you can call that atomic elements. It would be the rest of the elements in the periodic table. So that means all other elements. Okay. For example, if you write something like this, oh, Cu2, oh, that's wrong because it's not one of the 7 elements. We want you to memorize those 7. All right. What about you write something like, oh, Na? Can you write anything like Na2? No, because if it's not a diatomic, if it's not polyatomic, then it must be monatomic, or simply we call that atomic. Remember, both category 1 and 2, okay, both diatomic or polyatomic, they are so-called molecular elements, and for the atomic elements, they are monoatomic. Let's look at some examples. Which of these elements is a diatomic gas at room temperature? This question is actually more difficult than you think because there are 2 things you got to figure out. First, it must be diatomic. We do know rule of 7. When you look at the periodic table, you would be able to remember those 7 elements. But it also has another layer, which is it must be a gas. So for Br, we do know Br is a Br2. Okay, that's diatomic. Iodine is I2. Neon is not. it's atomic or monatomic. Chlorine is diatomic as well. Sulfur actually is SA. But out of the three, between A, B, and D, which one is correct? So you have to memorize this. Bromine is very famous elemental liquid at room temperature. So this one is liquid. Okay. Iodine actually exists in the solid. Iodine undergoes sublimation, and you will do this experiment in your lab, so that will actually impress you a little bit more. Okay. Chlorine is a gas in at room temperature. So D is the correct answer. Which of the following species is an atomic element? Remember, if it's not diatomic or polyatomic, then it must be simply atomic. So mercury is not diatomic, it's not polyatomic either, and this is an element. Mercury, by the way, is Hg, so that is an atomic one. And B, table salt, that's not even an element, that's a compound. Okay, oxygen gas, it's O2. CO2, that's a compound. H2 is diatomic. So that's why A is the correct answer. So we just gone over the details about elements. Now let's talk about compounds. For compounds, we have an ionic compound, which is formed between a metal and nonmetals. For covalent compound, or so-called molecules or molecular compound, they are formed in between nonmetals. Let me give you a few more examples. For example, what compound is this compound? First, we do realize that's a compound, that's not an element, because you have 1, 2, 3 different elements. So that must be a compound. And then you notice that potassium, K, is a metal, and the other two are nonmetal. So metal plus nonmetals, that means this is ionic. What about this compound? Oh, it's nonmetals, nonmetal, so this must be covalent compound. Covalent compounds do form molecules. That's why we call this a molecular compound. Let's sum this up. A pure substance can be classified as either an element or a compound. An element can be atomic or molecular. A molecular element could be diatomic, which is 7 of them, or polyatomic, 3 of them. And all the rest of the elements in the periodic table would be listed as atomic or so-called monatomic. About a compound could be ionic, which is usually made of a metal and nonmetals. A molecular compound is made of nonmetals only. Next, we are going to talk about how to name different formulas. Okay. Notice I did not say how to name different compounds, because not everything is a compound. Some formulas could be an element. For element, when you name it, you simply use the elemental name. For example, O2, that would be called oxygen or oxygen gas. N2, this is an element. We simply call that nitrogen or nitrogen gas. Here's another formula. For example, that's Cl minus. We're not going to call this simply chlorine, because chlorine means it's Cl2. This is actually chloride. Of course, we'll talk about how to name these things. Do remember, hey, I want you to always start with the type of formula. Do remember, not every formula is a compound. Cl minus, that's an ion. that's not a compound. Okay, give you another example. NO2, that's a compound. Okay, we'll talk about how to name that compound. But if this thing carries a charge, that's not called a compound. That's ion. Compounds do not carry charges. Compounds do not carry charges. Any species that carries a charge, that's classified as ions. And the cations are the ions that carry positive charges, and anions carry the negative charges. Okay. Ionic compounds is usually composed by, we learned this already, metal and nonmetals. Right. For molecular compounds, we have two different types. Actually, for these two, the last two categories, both of them are molecular compounds. Okay. However, one is called a binary molecular compounds. And acids, we have different types of acids as well. Okay. So let's talk about this first by looking at a few more examples. I can never overemphasize one thing. Before you start naming anything, you must always start with the type of formulas. Okay, so a few more examples. For example, what is this? Let's do that, yeah. What is this? Oh, let's say this is 1, 2, 3, 4, 5, right. So that's carrying a negative charge. It can't be a compound. So this is anion, or number 2, okay. But if I write something similar, what is this then? Oh, that is actually a compound because it's two different elements with no charge. So that is a compound. All right. Okay. By the way, not only this is a compound, this is composed of two different elements, 1 and 2. Okay. So this one, not only it's a molecular compound, it's also binary molecular compound. All right. What about this one? For naming purpose, all right? We are doing this for naming purpose. So apparently this one does not carry a charge and you have two different elements, so it must be a compound. But what type of compound for naming purpose? It's a metal and non-metal. So this is ionic compound. All right. What if I have something like this? Oh, H2SO4. Apparently that's a compound and it's not ionic. So what is this? It's not a binary molecule either. So what is this thing? Hey, you notice that this guy starts with the hydrogen. So that is actually an acid. So that's number 5. Okay? All right. What about HCl? When you look at HCl, by the way, for acid, usually you put AQ after that. This will make everything more clear because when HCl dissolves in water, it makes an acid out of it. Okay, so HCl, it is, when you look at that, it's 1, 2. It looks like you can classify this as binary molecular compound. But we single it out because this is a special type of binary molecular. It is an acid. It is binary, but it contains hydrogen to begin with. So that's why we call this a binary acid. So this is also number 5. Okay, but more specifically, this is binary acid. See, that's a binary acid. Then the other acid, like sulfuric acid over here, it's so-called oxyacid because it does contain an oxygens over there. Okay, so it's extremely important for you to know before you name anything. You must start with the type of formulas. If you're not able to determine what type of formula you have, you will never be able to name a formula correctly. So let's first talk about how to name cations. Then we'll talk about how to name anions. Okay. There are two different types of cations. Okay. Usually those cations will be metal ions. with one exception, for example, H+, that's not a metal ion, okay, but it also follows the name of the cations. By the way, this is called a hydrogen ion. Okay, the ion portion is required. You cannot drop the ion because hydrogen, that's hydrogen, which is diatomic. Okay, so if you don't say hydrogen ion, it's kind of confusing. Okay, I know sometimes you do hear some people call H+ just hydrogen, but it's not accurate. Right. So for metal ions, we have two different types. Not only you need to know what type of formulas you have, you also need to know the subtype, right? Which is really important. We have two different types of metal ions. One is called type 1 metal ions. Okay, type 1 metal ions, the reason they are named as type 1 is because you have invariant charge. You only have one possible charge when you exist in the compound. So that's so-called type 1 metals. And so what metal elements will be type 1? It is actually, you have to memorize it. It's group 1A, 2A, and 5 other elements. So if I rewrite it, there is another one which is controversial. Some textbooks indicate it, some don't, which is Sc or scandium. Okay, but at least these four, as you see over here, most textbooks would list it. So if I rewrite it, so the elements for group 1A, 2A, and the 5 other elements. Okay, why do I want to rewrite it? Because I also want you to know the charges. Okay, aluminum, zinc, cadmium, and silver. Okay, so the second thing, first you got to know this is a group 1A, 2A, and 4 or 5 other elements, depending on which textbook you are looking at. Okay, do remember for type 1 metal, you only have one possible charges. And the good thing about type 1 metals is you actually know what charges they will carry in the compound just by looking at the group number. Okay, if you look at your periodic table, please have a periodic table by you all the time. All right, so aluminum is in group 3A. We use the AB system. Okay, we're not going to use the 1 through 18 system, AB system. So group 3A, and this is type 1. So that's why this is a 3+ charge. Okay, for zinc, it's in 2B. 2B. Again, it's the AB system. So this is why this is 2+ charge. Cadmium is in 2B as well. Okay, so it's 2+. And silver is in 1B. See that? That's why it's 1+ charge. Okay, and all 1A, if they are positive charge, it will be +1 charge. 2A, it would be +2 charge. Do remember, type 1 does not mean, oh, everybody will carry 1+ charge. Wrong. It's not correct understanding. The correct understanding is type 1 only has one possible charge. Okay? All right. That's really important. And for this reason, because you only have one possible charge, there will be no ambiguity or confusion when you name the ion, because there is only one possibility. For this reason, we simply name this ion as an elemental name plus ion. For example, how do you name Zn2+? Oh, Zn, oh, you got to memorize that's one of the 4 or 5 that's listed as type 1. So you simply name this as zinc ion, sodium and sodium ion. As I said, do not drop that ion portion, because sodium means it's Na, that's sodium. Sodium ion, it's Na+. All right, so do not drop the ion portion. That's not the best naming. All right, for type 2. So type 2 ions will have a charge that can differ in different compounds. Or in another word, type 2 metal ions have 2 or more possible common charges when they exist in the compound. So that's why we name it as type 2. But do remember, similar to what we just emphasized for type 1 metal, type 2 doesn't mean the metal can only carry 2+ charge. No, it just means it can carry more than one possible charge. or 2 or 3 or more. Okay, all right. So it's more than one possible charge for type 2 metals. Since they can carry more than one type of charge, you might be wondering, so what are, how can I find out if a metal ion is type 2? So all other metal ions actually, if they are not type 1, okay, then they must be type 2. Let me actually change this. It should be a type 2, not type 1, okay? All other metal ions. All other metal ions will be type 2 metals. For example, if I give you something like this, Cu2+, how do I name this? First, you got to know this is a metal ion. Okay, metal ion, you got to know if it's type 1 or type 2. Oh, when you look at that, hey, this guy is type 2. Why? Not because you have 2 charge over here, so you call this type 2. No, it's because it's not 1A group. It's not in group 1A. It's not in 2A either. It's not one of the 4 or 5 I just mentioned. So that's why you call this type 2. Not because you have 2 charge. No, it's not because of that. Okay, so this is called a cobalt 2 ion. So why do we use a Roman numeral sign? Because if it's not type 1, that means you have other possibilities. Even if you don't know what the possibility is, you still know, hey, this guy has siblings. If you name the top one as cobalt ion only, then what about the brother or sister over here, the sibling over here? Oh, you call this cobalt ion? Then how can you tell apart the top and bottom? So that exactly tells you why. You got to find a way to tell them apart, which is use the Roman numeral to indicate the charge. Okay? All right, again, please use the ion to make this complete. Okay? All right, let me give you another example. If I give you something like this, for example, Au, by the way, Au is gold. If I give you plus, again, look at the charge. Don't look at the charge. Oh, what do you mean I look at charge? Don't look at charge. Hey, you look at, is this type 1? If it's type 1, it must be group 1A, 2A, and the other 4 or 5 elements. Apparently, this is not one of them. So this means that's actually type 2. Okay? Do not look at the charge to determine if it's type 1 or type 2. Okay? So this is type 2 because it's not a 1A, 2A, or the 5 other 4 or 5 elements. So this is actually gold 1 ion. Okay? All right, let's look at the one special cation, which is not included in the previous slide. Okay, this special ion is actually a so-called ammonium ion. That's a polyatomic ion. You will simply have to memorize it. It's NH4 plus. This is called ammonium ion. And we have a compound, which is NH3. This is called ammonia. Hey, remember, ammonia, this guy is a compound. This guy is a compound. Okay? And NH4 is a cation. So what is the formula for ammonium ion? The correct answer would be E. Okay? You simply have to memorize it. What about anion? For cation, you have type 1 and type 2. For anion, we have 2 different types, but we don't call that cation or anion. We call that a monatomic versus the polyatomic. For monatomic, here's how you do the naming. You keep the base and change the end into IDE. So if I use a line to represent the base, okay, and you have IDE over here, then you would be able to name it. Okay. So for example, fluorine, that's fluorine. Okay. So the ion, you just drop the end in INE and change it to IDE. This will become fluoride. But have you noticed we did not emphasize you have to call that fluoride ion? If you say fluoride ion, that's correct. But it's not required because nobody's going to confuse fluorine, which is F. More exact, the element would be F2 because it's diatomic, right? Okay, nobody will confuse fluorine with fluoride. That's why for anions, actually the ion portion is optional. It's not required. Okay, look at another example. For oxygen, again, the atom is O. The element would be O2, right? But again, when you write ions, you actually write the atom only. Okay, so you don't write O2. you write O, okay? Oxygen, OX is the base. Change everything else to IDE. That's why it becomes oxide, okay? Nitrogen, drop the ending or change the ending to IDE. It becomes nitrite, okay? All right. Another thing you might be wondering, how do I know what charge this is going to carry? Why is this -1? Why this is 2 negative, 2 negative, 3? Okay. For the monatomic anion, hey, remember for monatomic anion, you look at the way they look at the way they are located in the periodic table. Okay. The charge for monatomic anions, the charge equals the group number. What do you mean group number? It's AB system, -8. Okay. After you have learned the chapter 9, you will know this, because the elements would like to gain the corresponding number of electrons to become noble gas electronic structure. That's why. So this is group 7A. Okay. So that's why the charge would be 7 minus 8. That's how we know it's -1. So when we go back, if we ask you, hey, fluoride, of course, you know it's a base plus IDE. That comes from monatomic anion. You know it comes from fluorine. But what charge does it carry? Oh, we do know this is from group 7A, so it carries 1 negative charge. You only write the negative. You don't have to write that 1. That's how we know. This is extremely important when you try to go back from the name to the ion. For example, nitrite. Oh, how do I know it's N3 minus? Oh, first thing it's nitrite. NITR comes from nitrogen. But what charge does it carry? Nitrogen comes from group 5A. So the charge must be 5 minus 8, which is -3. But when you write the charge, you write the number first. So it becomes N3 minus. That's how you know it's N3 minus. Okay? All right. So we just talked about the monatomic anion. Now the second type of anion, which is polyatomic anion. Sometimes it's also called oxyanions because they usually contain oxygens. Not always, but usually they do. Okay? So for oxyanions, you have many different ways to do it, but I'm going to introduce to you a good way to speed up the memorization process. So you first want to memorize the 5 common oxyanions that have ATE endings: carbonate, nitrate, phosphate, sulfate, and chlorate. All these anions, you notice that they have ATE ending. ATE ending. You have to memorize this 5. They have different number of oxygens. Some have 3, some have 4. And the charges are different as well. So you simply have to memorize this 5 to start with. After that, things will become much easier for you. Okay? What we are going to do is, based on these ATE ending elements, we compare the number of oxygens with the ATE ending. So, if the oxyanion has 1 fewer oxygen than the ATE, so 1 fewer oxygen of what? 1 fewer oxygen than the ATE ending. So that's basically what this is. Okay? Then you use ITE. For example, if we remember, oh, PO4 3 minus. Then what is PO3 3 minus? Oh, don't try to remember the absolute number of oxygen. You don't think, oh, all 3 is going to be ATE or ITE. That's not the correct way to memorize. You simply remember the whole thing for the ATE. For PO4 3 minus, this is called a phosphate. Okay, phosphate. So you have 1 less oxygen, that would be called a phosphite. You simply change the ending from ATE to ITE. What if you have still 1 less? Oh, look at this example. You still have 1 less. What do you call that? You put a hypo before that, before this whole thing. Hypo means below. Okay? That means it's still 1 less than the ITE. All What if you have one more than ATE? You actually put a per before that, which means above. Okay, so perchlorate. So that's the 5 you need to memorize. And based on that, you will be able to write the correct names for them. Right. And one more thing I want to emphasize, if you have not noticed, did you notice that for the same series, for example, for NO series over here, okay, NO series, all of them have the same charge, one negative charge. For PO series over here, did you notice that all of them, no matter how many oxygens they have, okay, they have exactly the same 3- charge. SO series, look at that. Hey, that's all 2-, and all the other things, they carry in the same series, they carry the same charge. That's quite important for to help you memorize all these formulas. Okay, all right. The next thing we're going to talk about is, since now we do have the cations and anions, right? Can we put them together to make a compound? And that's exactly what we are going to do. Because an ionic compound is actually composed of a metal and non-metal. So the metal will form the cation, the non-metal will form the anion. When you put it together, we use so-called crossover rules. Okay, the crossover rules tells you you're going to cross over the superscripts or the charges, but without the sign. You don't put the plus or minus in. You never cross over subscript. The only thing you cross over is the superscript without the sign. So when you write aluminum ion and oxide, 2 is crossed over to the left side, and the 3 is crossed over to the right side, and they become subscripts. Okay. Do remember, the superscripts, when they become subscripts, you need to simplify them if it's not most simple. For example, if it's 2:2 ratio, as you see over here, you got to simplify to 1:1, which is not written over here. Okay. I'm going to give you another example. What if you have parentheses? Sometimes it could be confusing, right? For example, if you have Fe, okay, 3+, and you have PO4, 3-. So remember, never touch the subscript. You don't cross over the subscript. You cross over the superscript. So when I write Fe, just copy that without the ions, without the sign. Hey folks, remember, never put that 3+ in this formula. You see this formula. Never put the charges in the compound formula. That's simply wrong. If you write it this way to begin with, that's totally wrong, because a compound does not carry charge. That's why you don't want to put the charge inside the formula. So that's wrong. You don't write it that way. Okay. So what you should be writing is, so since we're going to cross this over, I'm going to rewrite this whole thing. And I copied Fe only without the charges. And I copy PO4 as a whole unit. All right. So this 3, number 3, goes to the right side. That's a number 3. Since PO4 is a group, you have to use a parenthesis. If it's one atom, you don't use parentheses. Since this is a group of atoms, you have to use parentheses. And the 3 on the right side goes to the left. That's a 3. But do remember, 3 and the 3 ratio is not most simple. That's why you simplify it. It becomes this. Notice that now PO4 only has one unit. For parentheses, how do you correctly use it? Parentheses are only used in case you have more than one group of atoms. Okay, so you only have one over here, so you don't write it this way. You actually need to rewrite it and write it as FePO4. That's the final answer. Okay, look at one example. So what is the formula between lithium and nitrogen? This question, it's 2 layers. When you look at group 1A, hey, do you remember group 1A is type 1, group 2A is type 1, and for other elements, if I indicate it's aluminum, it's zinc, it's cadmium, it's silver. Also for scandium, depending on which textbook Sometimes they include it, sometimes they don't. Okay, so these elements indicate elements. They are type 1 metals. And you know the charges. Lithium is this one. So you do know lithium will carry 1 plus charge. Okay, what about nitrogen? Oh, nitrogen, when it forms an anion, it's monatomic anion. Monatomic anion, the charges can be determined by the group number. When you look at nitrogen, oh, that's 5A. So the charge for nitrogen should be 5 minus 8. This gives you -3. Again, the charge is -3, but when you write anion, you write the number first. You see? So when you cross it over, the number 1, which is not written, I'm going to write it over here. 1 goes to the right side, 3 goes to the left. So Li is going to take that 3, N is going to take that 1. So that's why D is the correct answer. Okay. Hopefully by now you have a clear understanding of how to write the correct formula, as well as the naming of cation and anion. Cation, you have type 1 and type 2. Anion, you have monatomic versus polyatomic. And you must make sure you understand how to name a cation and anion, so you know how to name an ionic compound. Because an ionic compound is composed of a cation and anion. So to name the ionic compound, you simply name the cation and name the anion. Then you put it together after dropping the ion portion. So this, you basically need to get the ions. That's Na plus and the Cl minus. Na plus is sodium ion. Drop the ion portion. Cl minus is chloride, as we learned, chloride ion. So you drop the ion portion, that becomes sodium chloride. That's why you get that name. You see, remember, Na plus is type 1. So you don't call that sodium 1 ion, you simply call that sodium ion. That's why this becomes a sodium chloride. Okay. FeO3, remember, how do you do this one? Let's go over this in detail. All right. First, you do remember oxygen is monatomic. You know the charge for each one. So Fe2O3, you need to figure out, first thing, the ion. For Fe, iron, it's a type 2 cation. How do I know? Because it's not group 1A, not group 2A, not 4 or 5 other elements I ask you to memorize. So we do not know the charge. You have to calculate this charge. But oxygen, we do know it's in group 6A. Hey, look at the periodic table at group 6A. So oxygen should carry 6 minus 8. So we do know oxygen is O2 minus. So the charge for oxygen would be O2 minus. But what charge will Fe carry? So let's do the calculation. All right. Do remember this is a compound. The total charge is 0. So each oxygen is -2. Okay. This is each atom that carries the charge. The bottom one, I'm going to write the total charge. Total. So you look at total, 3 oxygens will give you a total -6 charge, because -2 times 3 is -6. So do remember, all compounds carry no charge. So to balance out the -6 charge, the total positive charge would be +6. So that's distributed amounts to 2. You see, 2 is a subscript for Fe, right? It's distributed amounts 2 ions. So each ion would carry +3. So that's how we know over here Fe would carry 3 plus charge, because we calculated this according to the neutrality of the compound. Okay, so the positive charge should be balanced out by the negative charge. So we do know it's Fe3 plus. Why do we need to calculate this charge? Because we know it's type 2 ion. We have to indicate the charge using Roman numeral. So for this one, we will call, because Fe3 plus is called iron 3 ion. Again, we're going to drop the ion portion when you name the compound. And the O2 minus is oxide. But we drop the ion portion. Remember, please drop the ion portion. So this whole thing is called oxide, iron 3 oxide. And this 3, you look at this 3, is this one. That's the charge that you indicate. Not 2. Hey, you don't want to name this as, oh, iron 2. Wrong. You cannot do that as iron 2. That's wrong. Because it's not a subscript. It is the charge that the Roman numeral indicates. Okay? All right. What about the next guy? So let's work on that guy. You always want to break it down into ions. Okay? So let's do it. Ca is in group 2a. If you look at your periodic table, hey, that's where my Ca is. Group 2a, that means it's a type 1 ion. You know the charge by looking at, oh, that's group 2a. So Ca must carry 2 minus charge. So for that reason, we can write this out. I mean a 2 plus charge. Sorry, not 2 minus. Okay, it's cation. All right. What about ClO? Oh, this one you will have to memorize it. ClO series all carry -1 charge, as I explained it to you. All the ClO series will carry exactly the same charge, which is -1 charge. Okay, for polyatomic anions, you don't calculate the charge based on the corresponding group number. You don't. You simply have to memorize for each series, like SO series is 2 minus, ClO series is going to be negative, PO series -3, stuff like that. Okay, all right. So you simply have to memorize that. So for this reason, that's how we do know ClO is going to carry negative charge. Okay, 1 negative charge. So you write out the ions. The calcium is called a calcium ion. Again, when you name the ionic compound, you drop the ion portion. Okay, so it becomes calcium. And the next one, polyatomic, that's called hypochlorite. You see that? That's called a hypochlorite. Okay, and then for the last one, we're going to work on it again. So do you remember PB is type 2? How do you know? Because it's not type 1. How do you know it's not type 1? Because you memorize what type 1 is. Okay, so sulfur is from group 6A. That's group 6A. So that's how you know it must be 6 minus A charge. That means a 2 minus charge. So that's why we do know sulfur is 2 minus charge. But what about PB? What charge should you have? Hey, remember PbS2. Each one is -2. So 2 sulfur will give you -4 charge. So to balance out the -4 charge, Pb is 4 negative charge, and it's 1 Pb or lead. So each lead will carry +4 charge. That's how you know it's 4 plus charge. And since Pb is not type 1, it's type 2, so you have to use Roman numeral. So you do know that's lead 4. The most common mistake is students do not include the Roman numeral or include the wrong Roman numeral. After we calculate it, we know it's 4 plus charge. That's why it's lead 4 sulfide, because S2 minus is called a sulfide, as we have already learned. So let's summarize this portion. To name an ionic compound, you must make sure this formula is an ionic compound to begin with. If it's an ion, name it after the ion naming system, like a cation and anion. If it's an ionic compound, or in another word, if it's a metal plus non-metal with no charges, that means you name the cation plus the anion, but drop the ion portion. Drop the ion portion. Okay, that's how you name it. Now let's go to the next category, which is binary molecular compound. Binary, what do you mean binary? Binary means you have 2 different elements. So basically it could be written as X and Y. Both X and Y, they are nonmetals. That's the first thing. Okay. And the second thing is you could have certain number of X, you can have a certain number of N as the subscripts. Okay, M and N are whole numbers. All right. So how do you name this thing? 4-step procedure. For the first element, you name after its elemental name. If it's carbon, you call that carbon. If it's nitrogen, call that nitrogen. The second thing, remember for the second element, you change the ending to IDE as if it's the monatomic anion. For example, if it's chlorine, you call that chloride. Nitrogen, call that nitrite. Oxygen, call that oxide. Okay. Sulfur, call that sulfide, etc. For this type of binary molecular compounds. Okay. The next thing is you always use prefix. Hey, remember, for ionic compound, we never use prefixes to indicate. We never say monosodium monochloride. No, okay? You never use that in ionic compound. But in binary molecular compound, we do use prefixes to indicate how many atoms you have. For example, you use mono to represent 1, di to represent 2, so 3 and 4. You got to memorize all these things, okay? All right. 6, hexa, etc. So basically, you have a prefix that you use, okay? But for the first element and the second element, would have IDE ending. You do have a prefix. But there is one exception. You do not use prefix, use a mono in the first element. For example, if I have CO2, hey, I know I have 1 carbon, but you're not going to say, oh, monocarbon. That's weird. It's not monocarbon. It's simply carbon dioxide. Okay? We're going to do another one. Right? For example, CO. How do you call CO? Hey, the first one is carbon, so you call that carbon. You don't say that monocarbon. The second one, you do use mono. We say the only exception is you don't use mono for the first prefix, okay? So you do use it for the second. But notice that we don't simply call that monooxide. We call this monoxide because we do have one more trivial rule, which is if you have OO, you actually change it to O. If you have AO, okay, you change it to O as well. So you have a pentoxide rather than pentaoxide. If you Google it, you can still see the old way like a pentaoxide, but now we use pentoxide. Okay? All right. Now let's put everything together and try to name this thing. Okay? And hopefully you can go, by going through these real examples, you'll be able to name these things with no mistake. Right? Recall, the first step to name any formula is to determine the type of formula you have. So the first one, oh, that's binary. How do you know it's binary? Hey, do you remember what different types of species we have over the different type of formulas? We have 5 major categories, right? Then we have subgroups. For example, we have ionic compound, okay? We have ionic compound. We have binary molecular compound. We have acids. But do remember, we also have cations and anions. That's 5 different. So cation, anion, that's a review, okay? Then you have ionic compound for naming purpose, all right? Then you have binary molecular compound. Binary molecular compound, some texts will also call it binary covalent compound. That's exactly the same, right? Then you have acids. Okay, we'll talk about acids in a little bit, okay? So the first thing, you got to determine what type of formulas you're dealing with, okay? So the first one is binary molecular. Binary molecular, do you remember, is a 4-step, right? So the first one is sulfur. We call this sulfur. It's 1 sulfur. We don't use mono as the first prefix. So this is sulfur dioxide. The second one, it looks so similar, but it's totally different naming system. Why? Oh, because the type of compound, that's where you should be starting with, is different. When you look at that, this is a metal, this is non-metal. How do I know if one is metal, non-metal? Refer to your periodic table. On the left side, except for hydrogen, to the left side of that zigzag line, okay? To the left side, that's metals. To the top right corner, plus hydrogen, that's non-metals, okay? So it's a metal plus non-metal. This would be ionic compound. For ionic compound, how do you name it? or you name cations and anions, which means we'll have to break this down into corresponding ions. For ions, though, you got to know which subtype. For example, SNO, what charge do you carry? If it's a type 1, you look at the periodic table, but it's not type 1 because it's not group 1, A2A, or the 4 other elements. But for oxide, we do know it's 2- charge. So how do I figure out the charge for tin or SN? You balance out the charge, right? So each oxygen carries -2. 2 of them carry -4. To balance out the negative charge, you should have +4. That's why we know it's 4 plus charge. So when you name this ion tin 4, do you say dioxide? No. Ionic compound, you simply name the anion, cation and the anion, and drop the ion portion. Put it together, it would be oxide. If you say dioxide, that's wrong. You don't put di, tri, whatever in ionic compound. In binary covalent, you do. In ionic, you don't. Okay. Look at the next guy. It would be dioxygen, not dioxide. Okay. The first one, it's the element, so it's dioxygen. Okay. Then 7 is hepta, but it's a heptaoxide. So AO, it becomes heptaoxide becomes heptoxide. Similarly, for the next one, we don't say monochlorine because we don't use mono for the first prefix. Hey, to remember, yeah, I should have just should not skip that. This is binary covalent. That's why we name it that way, okay? Or binary molecular, which is exactly the same. Binary molecular compound. This next guy is also binary molecular. The previous one this is binary molecular. The next one is binary molecular. So that's why for chlorine, let me write it right over here. We don't use mono for the first one, so it's called a chlorine. The first one name as is dioxide. Right. We always start with the correct type of formula to begin with. All right. Carbon monoxide, dinitrogen monoxide, tetraphosphorus. 10 is octa, is deca. Okay, so decoxide. So this guy is tetraphosphorus. Phosphorus decoxide. Not decaoxide, although we still recognize, yeah, we still say, yeah, we say it's okay, but usually we call that decoxide rather than decaoxide. Okay, look at the last one. When you compare this two, you say, yeah, yeah, I'm gonna name it the same. Yeah, so it's chlorine dioxide ion. No, hey, ions have totally different naming system. You cannot just simply add an ion after ClO2 naming. That's wrong. So for the ion, this is oxyanion. Okay, not only it's anion, it's oxyanion. For oxyanion, you compare these anions with the corresponding AT ending. If it's one less oxygen in that ion, okay, then you change ATE to IT. If it has still one less, you put a hypo before that whole thing. Okay, if you have one more than AT ending, you put a per before the whole thing. So this guy has one less than ClO3, which is so-called a chlorate. So this is chlorite. Okay. So this is oxyanion is the type. So this guy is named as chlorite because it has one less oxygen than the ATE ending. Okay. So hopefully this will clarify some of the mistakes you might have. All right. Next, we're going to talk about the last type of compound for naming purpose, which is so-called acid. Looks like everything comes in couples, right? For acids, we also have two different types. One is called a binary acid. So basically, what is an acid? Acid starts, okay, an acid will always start with hydrogen. Remember, hydrogen. So if I give you something like this, HgNO3, is this an acid? Is this an acid? No. Hg is actually the first element. This guy is mercury, not hydrogen. So some students, when you look at, oh, I have a H over there. No, it's not the letter H. It's the hydrogen element, okay? It starts with hydrogen. So for example, HCl, oh, that's an acid. H2SO4, that's an acid. And we have two different acids. The first type of acid is so-called binary acid, which means you have two different elements, right? Binary acid, what do you mean binary? Binary means you have hydrogen, of course, it's an acid. You must have hydrogen, and you also have another element. So you can have certain number of hydrogen, okay, subscript M is a whole number, right? For example, hey, you have H2S. Hey, that's the example, okay? You use AQ to represent it's dissolved in water. So what about HCl? Yes, AQ over here. So how do you name it? The name is always hydro whatever ic, see, acid. So if I want to rewrite it using a blank to represent the base for that X, okay, for this X, that's the base for that X. It's hydroic acid. You see that? So we can name this, accordingly. Hey, it's always hydroic acid. Hydroic acid. So Cl is chlorine. So it's hydro. You drop the INE and you put ic acid. You see? So that's why it becomes hydrochloric acid. Okay. Similarly, you have hydrobromic acid, hydrofluoric acid. Okay. For H2S, you don't call that dihydro. Remember, it's always hydro whatever ic, no exception, even if you have more than one hydrogen. Okay. But to remember, it's binary acid. Okay. That means you have no oxygen inside. So this guy is called hydrosulfuric acid. Hydrosulfuric acid. I do want to mention one thing over here. All right. In the acid, the base for sulfur is actually sulfur, the whole thing. Still remember when we talk about SO4 2 minus, right? Which follows a totally different naming system. Okay, you can review that. This is called a sulfate. You see, apparently SULF is the base, but in acid, it's the whole thing, sulfur as the base. It's slightly different. I hope you actually noticed that. So again, H2S, that's called a hydrosulfuric acid. It contains no oxygen over there. If it's H2SO4, that's not a hydrosulfuric acid. It's actually a different type of naming system, which we are going to talk about right now. H2O4 is a type of acid that is called oxyacid because it contains oxygen. If you have oxygen inside, the naming is based on the corresponding anion. Okay, for example, if the oxyanion or the polyatomic, right, polyatomic anion, okay, or oxyanion, if it has ATE ending, you change ATE to ic and keep everything else untouched. Okay, all right. If oxyanion has ITE ending, then you change the ending to OUS acid. Okay, so let's look at some examples. For example, how do I name this guy? You can cover the right side to begin with. Okay, then you break this down to the corresponding ions. And the anion portion, of course, you have H plus. Okay, the anion is NO2 minus. NO2 minus is called a nitrite. Okay, so remember what's the ITE ending? You change ITE to OUS acid. That's why it becomes nitrous acid. Okay, and this guy, when you look at that, it becomes H plus NO3 minus. Hey, nitrate. Hey, this guy is called a nitrate. That's why when you go back, it becomes ic acid. ATE ending for the corresponding oxyanion. Change that to ic acid. It's always the same way. Okay. I'm going to give you a special example. For example, how do you name this guy? So how do I name it? I look at the corresponding anion, right? H plus, of course, you always have it, okay? But the anion, this thing, anion, this guy is called a perchlorate. We learned this already because it has one more oxygen than the chlorate, okay? So it's ATE ending. So for the acid would have a name that changes with the ATE being changed to ic acid. So the acid is called a perchloric acid. Okay, let's sum it up. Basically, for oxy acids, you look at the corresponding oxy anion. If the oxy anion has ATE ending, change ATE to ic acid. If it has ITE ending, change the ITE to OUS earth acid. And everything else stays exact the same as the original oxy anion. All right. Okay. So this next slide actually tells you a few more examples, which has all kinds of examples. This one, what is that? Oh, you got to first determine the type of compound. Oh, this is binary molecular compound. Oh, you go by the binary 4-step procedure. Okay, so that's why it's called a carbon monoxide. The second one, oh, it's metal plus non-metal. So this ionic compound. Ionic compound, you name the corresponding cation and anion, put it together, and then take away the ion portion. So calcium ion plus the fluoride ion, it's calcium fluoride, not calcium difluoride, because for ionic compound, you don't use the prefix. In binary molecular, you do. All right, okay. Now look at FeNO3. How do you know this guy? To remember for monatomic charges, you actually look at the corresponding group number, but the NO3 is a unit. You don't look at the individual one. You simply memorize, oh, NO series always carry one negative charge. The whole thing is one negative. So 3 of them would be -3. To balance out -3 charge, you have to have +3. That's why it's called iron 3. Okay, why do you use 3 for this one? Because iron is type 2 ion. Okay, iron 3 nitrate. All right, and you can look at the other couple of examples which I have already discussed in great detail. Okay, now let's move on to a different topic, which is now you know how to write the correct formulas, how to name the formulas. Do we know how to calculate the formula mass? How do you calculate the formula mass? You simply total up all the atomic masses, okay, atomic masses. Then you have the formula mass. So for example, in carbon tetrachloride, you have 1 carbon. So if I write this thing, so this basically is 1 carbon plus 4 chlorine. So when you write down carbon, when you look at your periodic table, is 12.01. And the chlorine, each chlorine is 35.45. Put it together, it gives you 153.81. All right. Now let's look at another example. So what is the formula mass for sodium sulfate? You must be able to correctly write sodium sulfate. Sodium, you know, sodium, that's a metal. Sulfite, okay, not sulfate, sorry, yeah. Sulfite, it's an anion. Okay, when you put it together, you have cation and anion. When you try to put it together, you must be able to use the crossover rules, crossover the charges. So it's Na2SO3, which carries the one that is not written. So now you write the correct formula. Okay, so the formula mass is it count the correct number of atoms. We know how to do it, right? So this is how many sodium? It's 2 sodium plus 1 sulfur plus 3 oxygen. Okay, now you put it together. This gives us C as the correct answer. Let's look at one more example. What is the formula mass for ammonium sulfate? This time we actually give you the formula to begin with. So how many nitrogens do you have? How many hydrogen, sulfur, oxygen? So we write this together. Formula mass would be 2 nitrogen. Hopefully you know how to count it right now, okay? Plus, okay, 8 hydrogen, 1 sulfur, and 4 oxygen. Not 40, but it's 4 oxygen. So if you put it together, we will have D as the correct answer. So this concludes chapter 5. Thank you very much, and see you next time.